Okay, I think we can start. Right. Welcome everyone. Herzlich willkommen. Welcome everyone to Harvard CMSA Quantum Matter in Math Physics Seminar Series. We are very happy to invite Gerald Höhn and Sven Möller. They will be speaking about some exciting recent work. Several groups of people are working on something related on this conformal field theory with certain constraint on the chiral central charge and primary fields bound by 24, for example. And Gerald and Sven will speak today, and there will be some other following works by other group of people. And let me remind the audience, please feel free to ask questions, interact with the speakers, especially the experts. Please feel free to ask questions. Okay, so let us directly welcome both of them. Yeah, please take over. Thank you.
Yeah, thank you very much for the invitation to the Quantum Matter in Mathematics and Physics seminar and the opportunity to present the results which I have achieved with Sven Möller. So there were, as you mentioned, several groups who recently studied the problem of classifying self-dual vertex operators, superalgebras of central charge 24 or less, or in the physical terms of purely chiral two-dimensional and fermionic conformal field theories. So there were two physical groups from mathematics physics, Smith, Lin, Tashikawa, and Sheng, and Höhn, and two other groups, namely myself and Möller, and there is also a group by Kraul, Mason, Tuit, and Jans Kulnar, whose work is in preparation and who have a slightly different approach to the problem. Now, so the classification approach of myself and Möller is motivated mostly by mathematics. And so what I like to do in my talk is first to give an historical overview of the problem and explain my mathematical motivation why we did do this classification. So there is an analogy between codes, lattices, and vertex operator algebras, which allows to transfer results from one of the theories to another. And it's not just an analogy between methods and general results. There is also an analogy between distinguished objects. And so the most distinguished objects for coding theory, lattice theory, and vertex operator algebras are the Golay code, the Leech lattice, and the moonshine module, which have the sporadic simple groups, the Mathieu group M24, the Conway group, Conway 0, and the monster as automorphism groups. Now, besides this interesting symmetry group, these objects are also extremal in a certain sense in dimension 24, where dimension means for codes length, for lattices length, and for vertex operator algebra central charge. Now, these three objects, they are even objects, which means in the sense of binary codes doubly even. In lattices, one calls it even, and for vertex operator algebra bosonic. But it's also natural to look at odd objects, so which are fermionic or vertex operator superalgebras in the case of vertex operator algebra. And so one may ask what all these objects are. Now, let me start by binary or codes in general. So the reason why I became interested started probably by a work in 1982, which is based on idea of Manin, and this work constructed for the first time codes which were better as the Gilbert-Warshaw bound, which is a lower asymptotic bound for codes, which is rather trivial. You eventually just choose randomly code words to get good codes, but this paper for the first time constructed codes which were better than this Gilbert-Warshaw bound. And I think this was the reason why there in 1985 gave a lecture at Harvard University about rational points on curves over finite fields, which where the motivation was the connection to codes. Now there, it was not the first time that he contributed to coding theory. There is the connection from codes to lattices, which is also called the Prue-Enghart map, which was defined in a paper in 1972, which associates to self-dual doubly even codes, even unimodular lattices, and then relates the weight enumerator of the code with a theta series of a lattice. And it seems that this is also due to there, since in the footnotes the authors remark this homomorphism was pointed out to us by there. Now there discusses also unimodular lattices in his book, A Course in Arithmetic, and there he thanks actually John Milner in a footnote for the approach. Now, the reason John Milner was interested in unimodular lattice is because they arise in topology as the intersection form on the middle cohomology. But they also play a role in algebraic geometry, for example, Picard lattices of K3 surfaces. I mention here Nikulin because he developed a theory of gluing lattices together, and it turned out that this theory, this is part of our approach. Now, why was the lecture of there important for me? This was because my advisor, Hirzebruch, he followed somewhat closely Serre's work. Remember that starting from his PhD thesis on rational homotopy groups of spheres, which Hirzebruch then used to, together with the cobordism results of Thom, to prove the Hirzebruch signature theorem and then the Riemann-Roch-Hirzebruch theorem. So he was interested always in their work, and so Hirzebruch became also interested in coding theory, and he was also interacting with Niels Sloan, where it seems that Sloan found a connection of self-dual codes over the field with 5 elements with the work of Hirzebruch on Hilbert modular surfaces. And so what Hirzebruch and van der Geer could achieve was that they could generalize this Prue-Enghart map from binary codes to integral lattices to codes over a prime field over Fp to lattices over a certain ring of integers. Namely, this is the ring of integers in the total real subfield of the P cyclotomic field, where P is the code which over Fp, which you are considering. And so one associates then a code over Fp, a lattice, and it's the Lie weight enumerator of this code is related to the theta series of the lattice, and it gives Hilbert modular forms. Now, what I did some time later was that I generalized codes over the field F4, which were usually by all authors considered as linear codes over F4. I found it more naturally to look at these codes as actually codes over the Kleinian 4 group Z2 cross Z2, so the additive group of the field, and instead of the multiplicative structure of the field F4, one better uses a natural finite quadratic form on this space. And so it's what I then could do when I looked at codes over finite quadratic spaces, I gave a map from Kleinian codes of length n to binary codes of length 4n, and this map generalized somehow this map of Prue-Enghart from binary codes to integral lattices and later to vertex operator algebras. Actually, my viewpoint in this paper at the end was that one should look at codes over three-dimensional topological field theories which arise from representation categories of vertex operator algebras, as Witten has explained in his work on the quantum field theory and the Jones polynomial, where he explained how one could use Chern-Simon theories Wessomino-Witten models to get Chern-Simon theories. So in this viewpoint, one looks at the vertex operator algebra for the D4 lattice, which one associates the vertex operator algebra to the A1 lattice, then the Heisenberg vertex algebra, and then the Virasoro algebra. Okay, now let me give you some more details. So let me start with doubly even self-dual codes.
Really naive question. Just previous slide. If these are finite group gauge theory, why don't we use just Daigo-Witten type of a group cohomology gauge theory instead? I think you repeat. Yeah, I said that if we consider the finite group gauge theory here, like then why not consider?
No. One can of course do this for finite groups, but this here is more the abelian groups. So these are essentially simple current extension. So it's not finite group gauge theories, but more general. But you could of course also take a finite group gauge theory. That's correct. Yeah. But here, these are not, they may be also arise in this way, but the viewpoint was here essentially those where you have simple currents.
And also Witten paper is 89, right? It's 1989.
Witten could be that I made a mistake here.
Oh, thanks.
So the binary code here is a linear subspace over the field over the vector space over the field of two elements. But in coding theory, you are fixing the canonical base of F2 to the n and the canonical scalar product, and then one has the notion of weight, which is just the number of ones in a vector, and this makes F2 to the n into a metric space homogeneous base or more general an association scheme. So that's the essential structure which one needs for coding theory. And then one can define the notion of self-dual doubly even codes. These are self-orthogonal code with respect to this canonical scalar product of the maximal dimension n½ consisting of vectors of weights where all weights are divisible by 4. And so one is interested in coding theory in the minimal weight of a code, which is the smallest weight of a vector which is not the zero vector, and then one likes to have this minimal weight as large as possible. So in particular, one can look at doubly even self-dual codes, and then one calls such a code extremal if the minimal weight is as maximal as possible, this number. Now, there are only 2 extremal codes of a length, a multiple of 24 known. This is the length 24 Golay code, and for length 48 there is the quadratic residue code of length 48. Yeah, so the binary Golay code can be easily described by giving its generator matrix. So that's a 12 times 24 matrix, and the black dots represent ones. So the matrix is obtained by taking the 12 by 12 identity matrix, and this 12 by 12 matrix is the you taking the incidence matrix of the 12 vertices of the icosahedron, and then you take the complement graph, and so the adjacency matrix of this complement graph is this matrix. Now, I mentioned here 3 people, Mathieu, Witt, and Golay, because the automorphism group of this code is the Mathieu group M24, which was already found by Mathieu in the 19th century. Then Witt studied in 1938 the minimal vectors. There are 759 minimal vectors in the Golay code, which has the property that when you take 5 arbitrary positions, then they are contained in a Unicode word of weight 8, and the actual code was found by Golay in 1949. Now, one can ask now not just about extremal codes, but one can ask, how does the classification look for all codes? Now, for a doubly even self-dual code, it turns out that the length has to be divisible by 8, and then the classification up to n = 24, which is in a paper by Sloan and Pless from 1973, but they thank Conway and mentioned that he had done it before. It turns out that there are 1 code of length 8, that's the extended Hamming codes, 2K codes of length 16, which are 2 copies of the Hamming code, or code D60 plus, and there are 9 codes of length n = 24. I think they also later classified the codes of length 32. There are about 85 or so. Now, the 1 is the extremal Golay code, and all the other codes contain roots, which means in the sense of codes that they have code words of weight divisible by 4. So this is a situation for even codes, which one calls for codes doubly even, and the weight is divisible by 4. Now one can ask the same question for odd self-dual codes, which means that
I have a question.
Yes.
Is this classification related to the classification of the even marginal lattices over the integers?
Yeah, of course. I mean, this is what I came later to, but so it's a step before. You could, of course, say that even the classification of by Shellacant of the vertex operator algebras give you later this classification, because the reason is that this maps going from codes, lattices to vertex operator algebras, they are injective. So when you have done the work for lattices or for vertex operator algebras, you can go backwards to get the classification results for code. Now, this is maybe not the best way, because they, for vertex operator algebras, for our, we don't know how to do this. So it's better to look independently and look at coding theory as its own theory and develop methods there, and then later generalize them to lattices and vertex operator algebras. Anyway, it's not so hard. So this is some simple combinatoric, and probably Conway has done it in 5 minutes. Yeah, so for the odd codes, now I couldn't find a picture for the odd binary code, so I only found a picture for the odd Kleinian codes from one of my papers, and so I gave, so this odd codes, lattice and vertex operator algebras are best described by a graph. Namely, the edges of this graph are the odd codes here, and the vertices, they are the even objects. And so one get from an, when one has an odd code, then what one can always do is to look at its even subcode, which is a code of index 2, and then there are actually three extensions. One is to an odd code, and the others are to even codes, and these are the two endpoints of the edges. So in this way, one gets a graph which visualizes the classification of odd, binary codes. Now, I didn't have couldn't find a picture for the binary codes, and so I used the picture for the Kleinian codes. But since this map is injective, so this is a subgraph of the graph which one gets for the odd self-dual binary codes. Okay, so much about codes. Let me then continue with lattices. So a lattice.
Actually,
yes.
Related question. Maybe because you show some figures, I'm not sure I understand the figures. Like even 2 slides back.
This one.
That, maybe 2 more. Yeah, one more previous one. Another one. Yes. So what's this picture try to show? Is that also unimodular lattice formal? No, sorry, the one before. The one after. Sorry, the next slide.
This one?
No, the one after and after, 2 pages after. Next one. What's this? Can you explain?
So this is the neighborhood graph of the self-dual Kleinian codes here of length n equals 6, which corresponds then for binary codes of length 24. So again, the edges are the odd self-dual codes, and the nodes or vertices are the even self-dual codes. And the way this graph is defined is one takes an odd code, self-dual code, which has always an even subpart, which is a subcode of index 2. And then there are 3 different ways to extend this subcode of index 2. And one is to get the self-dual odd code, and the other 2 extensions are one gets even self-dual codes. And this even self-dual code, they are the two endpoints of an edge. So that's the way this graph is defined. So this is somehow a way to visualize the classification, but also gives you already a hint how you can classify the odd code. What you have to do is here you have to look at the nodes and check what are all the subcodes of index 2. When you can do this up to equivalence, then you would be able to classify all the odd self-dual codes.
Thanks. I actually was asking maybe 2 slides back. No, one slide
okay, but maybe I will explain more or less the same thing in the language of lattices and then in the language of vertex operator algebra. Maybe then it becomes more natural to understand.
I think you were looking for an explanation of like the table giving the basis for the Golang code.
I have problems to understand this.
Oh, like the table giving the basis for the Golang code?
Binary Golang code.
Yeah, so this is a basis which gives it's a 12 times 24 0-1 matrix, which is a generator matrix of the Golang code.
And what the field one and what the empty one implies?
Empty is 0, filled is 1.
What do you mean with empty? So the root system is, I mean here, this kind of root system, this would be empty for the Golang code. Okay, so maybe it becomes clearer when I explain you more or less the same story, but this times in the language of lattices. So a lattice is a 3 abelian subgroup of rank n in Rn, although one doesn't really need the embedding. Then one defines the norm, which is the analog of a weight, as a squared length of a vector. And then one says that a lattice is unimodular if the volume of a fundamental domain is 1, and the lattice is even if the lattice all lattice vectors have even norm. So if you have an even lattice, this automatically implies that this lattice is integral. And then similar, one defines the minimal norm of a lattice vector as the of lattice as the smallest length of a lattice vector besides the 0 vector. And then again, for certain problems, one is interested in, for packing problems, for example, one is interested in extremal lattices, and these are lattices where the minimal norm is as large as possible, which means in the case of unimodular lattices that it equals to this number, and in this case, what is called an extremal lattice. Now, for lattices of rank 24m, extremal lattices are known for rank 24, 48, and 72. For rank 24, we have the Leech lattice. For rank 48, there are at least 5, and for rank 72, there are at least 1. There may be many more. It's completely unknown. What one knows is that around rank 100,000 or so, the extreme lattices don't exist anymore. Now, the Leech lattice. So the Leech lattice, which was first constructed by Leech, but possibly also by Witt already in 1940, is an even unimodular lattice of rank 24, which has minimal norm 4. And it became then more famous when Conway showed 1968 and 69 that the Leech lattice is the unique extremal lattice of rank 24. And in addition, its automorphism group, which is called now the Conway group, Conway 0, modulo its center, is a sporadic simple group. Now, I gave you a generator matrix for the Golay code. The Leech lattice is also simple to construct. So one can construct the Leech lattice as what is called a laminated lattice. So one starts with a one-dimensional lattice, the sphere packing balls of radius 1 centered at the lattice 2z, and then inductively for each dimension one constructs a lattice in one dimension higher by stacking the densest lattices which one obtained by this procedure in one dimension lower together as dense as possible, and this gives then the lattice in the next dimension. Now this procedure is actually not really unique, at least not in all dimensions, but when you reach dimension 24, you reach a unique lattice, and that's the Leech lattice. Okay, similar as for the doubly even self-dual codes, one can ask for the classification of even unimodular lattices, and so the classification for 8 and 16 is not so hard. For n equals 16, this was done by Witt in 1914. There are two lattices, two copies of the root lattice E8 and an extension of the root lattice for D16. E8 was probably already known by Smith 1867. Also, he didn't construct the lattice, but he had a mass formula, so he could conclude that such a lattice existed. And then, as you mentioned already, Niemeyer, which was a student of Kneser, he classified all the all the even unimodular lattices in rank 24. And so besides the Leech lattice, he found 23 other lattices, and the methods which he used, this was eventually also the idea of the neighborhood graph, which I show you here in a second. So because Kneser has shown that when one goes to sub lattices of index 2 of an even unimodular lattice, and then such a lattice has two possible extension, and if one looks at this graph, then this graph actually has to be connected. And so it was clear that with this method, in principle, one can construct all lattices, and this is what Niemeyer did in 1968. Now, Borchardt, in his thesis in 1984, extended this approach and actually used it to classify now the odd unimodular lattices of rank 24. And again, the idea is that to classify the odd unimodular lattices is that by looking at the even sublattice, which is a sublattice of index 2, there are three ways to extend the sublattice. One is to go to the odd unimodular lattice, and then there are two other neighbors, the even unimodular lattices, and so in this way you get a graph. And so Borchardt classified all these lattices. Now this graph actually is just again only a subgraph, because he omitted several loops from this diagram which come from odd lattices which split off the integer lattice set as a direct summand, because these lattices, they always give loops, so they somewhere live in smaller dimension. Okay, so much what I like to say about codes and lattices. And now I come to vertex operator algebras. Now I will not give you a definition of vertex operator algebras. I just mentioned the paper by Belavin, Polyakov, and Samolochikov, which is considered as a foundation for the two-dimensional conformal quantum field theory. And I mentioned the two papers from Paul Ginsberg and Peter Goddard, where I learned this conformal field theory from the physical side. On the mathematical side, there was a paper by Borchardt in 1986, which defined actually vertex algebras and also sketched the proof of the moonshine module. And Frankel, Lepowski, Muirman in 1988 wrote a book where they gave a mathematical foundation of the theory of vertex operator algebras. Now, one should consider vertex operator algebras, or equivalently chiral algebras of two-dimensional conformal field theories, as the even similar to even lattices. Now, then one can say that a vertex operator algebra is called self-dual or meromorphic or holomorphic if it has only one simple module up to isomorphism. And then one can again introduce the notion of an extremal vertex operator algebra, as I did in my PhD thesis in 1995. And but it turns out so far there is only one extremal vertex operator algebra known for central charge, which is a multiple of 24. And this is the moonshine module. So as I mentioned already, the moonshine module, the construction was sketched already by Borchardt in his 1986 paper, and then full details were given by Frankel, Lepowski, Muirman in 1988. So the way the moonshine module is constructed, or at least the easiest way, is that one takes the vertex operator algebra associated to the Leech lattice and then takes a minus Z2 orbifold corresponding to the -1 automorphism of the Leech lattice, which one can uniquely lift to the Leech lattice vertex operator algebra. Now, before the moonshine module was constructed, Kreis constructed a 19688 4-dimensional algebra, which is called the Kreis algebra, and he showed that the monster simple group acts on this algebra and thereby actually constructing for the first time the monster. Then later Tietz showed that this is actually the full automorphism group of the Kreis algebra. And so this Kreis algebra is the degree part of the moonshine module. And Frankel, Lepowski, Muirman also showed that the full automorphism group of the moonshine module is the monster. Now, what is known for the classification of self-dual vertex operator algebra? Again, for central, one has that the central charge of a vertex operator algebra, of a self-dual vertex operator algebra, has to be divisible by 8. One can prove this, for example, by using the characters, which are modular function, and then properties of modular functions. So for C equal 8 and 16, one gets again that the lattice vertex operator algebras associated to the even unimodular lattices in this dimension give you the VOAs. This is relatively easy. And then for interesting question arises: what happens for C equal 24? And Schellekens in 1992 gave the answer. He found 70 vertex operator algebras, which are determined by the affine-Kac-Moody subvertex algebra. And there is a moonshine module. Now, the classification result of Schellekens was correct, but it was mathematically somewhat incomplete, since it did not really fully mathematically rigorously establish the existence and the uniqueness of the vertex operator algebra in all cases. And it took about 25 years to make Schellekens' result rigorous. Besides, for the moonshine module, which is still not known if this vertex operator algebra is unique. Okay, so this is a long introduction. Now I come to the self-dual vertex operator superalgebras. And so again, the idea is to define the two neighborhood graphs. If we have a self-dual vertex operator superalgebra of central charge a multiple of 8, we can look at its even or bosonic subvertex algebra, and then this subvertex operator algebra has 4 irreducible modules of conformal weight 0, 1/2, 0, 0, and so one can extend it by V1, which has conformal weight 1 and gives you mod 1 and gives you then a vertex operator superalgebra, or you can extend it by the 2 other modules, which will give you 2 self-dual vertex operator algebras, WA and WB, and you also have involutions acting on this vertex operator algebras, namely the involution which is -1 on the extended module and 1 on V0. And so you have a graph where the edges are the vertex operator superalgebras, and the end vertices of an edge are the vertex operator even the self-dual vertex operator subalgebras. And now for the involution, it depends only on the conjugacy class, which subvertex operator algebra you get. So what one has, therefore, is that the isomorphism classes of self-dual supervertex algebras of a central charge C are in 1-to-1 or 1-to-2 correspondence with pairs consisting of a self-dual vertex operator algebra of central charge C and a conjugacy class of involution in the automorphism group of the vertex operator algebra. Now, not every involution is good, because there are 2 types of involutions of type 0 and type 1. For type 0, the 4 modules of the fixed point vertex operator algebra have conformal weight 0, 1/2, 0, 0, but for type 1, they have 0, 1/4, 3/4, and 0, and so you cannot extend them to a self-dual vertex operator superalgebra. So one has to restrict to type 0. So in principle, one can now solve these problems by looking at the conjugacy classes of involutions of the automorphism groups for the 71 Schellekens vertex operator algebras. Now, this is not so easy when you look at the description of these vertex operator algebras by Schellekens, who did describe them as an extension of affine-Kac-Moody vertex operator algebra. And so what we then used instead is a lattice description of Schellekens vertex operator algebras, which I introduced a few years ago. So let me first describe the general idea. So what we like to do is somehow, when you have an arbitrary vertex operator algebra, I like to split of bosons, or more precisely, one looks at the so V1, the degree 1 part of a vertex operator algebra is a reductive Lie algebra, and then there is a maximum abelian subalgebra. It's Cartan subalgebra, so one can fix one, and then this Cartan subalgebra generates D bosons if it has rank D in the vertex operator algebra sense. And so now one can decompose the vertex operator algebra by taking the commutant of this Heisenberg vertex operator algebra, and one can also take the bicommutant, which is an extension of the Heisenberg vertex operator algebra and the lattice vertex operator algebra. And then when one so one has then that this lattice vertex algebra and this commutant W that form kind of a dual pair in this vertex algebra, and one can decompose the vertex operator, every sufficiently nice vertex operator algebra in this way by combining the modules of the lattice vertex operator algebra, which are given by the dual lattice modulo the lattice, and this is a simple current with certain modules from this commutant W. So this works for every vertex operator algebra. Now for self-dual vertex operator algebra, this situation gets better. So in this case, the lattice vertex operator algebra and the vertex operator algebra of the commutant, they are have isomorphic representation categories, at least the vertex operator algebras, and so one has to clue therefore a lattice with a lattice L with a vertex operator algebra W, and so this is done by looking at the induced action of the orthogonal group of the lattice and the induced permutation group of the vertex operator algebra on the irreducible modules or on the discriminant group of the lattice. And then one uses essentially this description which was in Mikulin's paper, and so one gets that that self-dual vertex operator algebra can be described by a genus of a lattice in the genus, a vertex operator algebra in the complementary genus which has trivial Lie algebra, and double coset in where one takes the orthogonal group of the discriminant group of the lattice modulo the action from the left and the right of these two groups here. So I did this in my paper, and so for this one has to figure out what the lattices and what the vertex operator algebra W are, and I conjecture that all this W can be obtained as certain fixed point lattices of certain co-invariant lattices of the Leech lattice vertex operator algebra, and I gave 11 explicit classes in the Conway group. So for half of them, although it was known that they have the correct properties, but it was then proven by Lamb that they have always the correct properties. And then also Lamb and Shimakura and Betsumaya determined finally the groups, the automorphism group of W and the induced permutation group on its module for all 11 cases, and then showed that my coset description really gives you the correct description, which I had already described in my paper. So here this gives you some information about, so they're altogether 12 dual pairs which one has to consider. There's always the unique vertex operator algebra W, and then there's a lattice in the genus. Usually the cluing is unique, but in the case of genus D and J, there are several double cosets. Okay, now we are almost done. So we know now from this group, the automorphism group of W and the induced permutation group of the irreducible modules, one can now compute almost the automorphism group of these Schelekens VOAs, because it consists of two parts. One has the inner automorphism, that's the connected component of the automorphism group, which is a complex Lie group, and then one has the outer automorphism group, which is a subgroup of the outer automorphism group of this connected Lie group. And knowing our W and the automorphism group of the lattices allows them to compute the outer automorphism group of V. However, this is still not enough, since this sequence doesn't split, and so even we have the inner automorphism group and the outer automorphism group, we don't have yet control over this group, and we also cannot really decide when an involution is of type 0. So there is a final other input which we used is we have to know now, when we go back to vertex operator superalgebras, we look at the even subvertex algebras, and we can also use the lattice description, which I've given you before, and I did say it holds for an arbitrary vertex operator algebra. We can also look at this for this even subvertex operator algebra, and then again the question arises which vertex operator algebras W as a complement of the lattice part arise in this situation. And this was conjecturally answered by Borchardt, because in his paper on monstrous moonshine associated to the moonshine module, but it works for any C equal 24, but self-dual vertex operator algebra, a generalized Kac-Moody algebra. Now this I generalized in a paper which proves the generalized moonshine for the baby monster to self-dual vertex operator superalgebras. I did it only for one super vertex operator algebra, but this proof works for all. And so one gets for each self-dual vertex operator superalgebra a generalized Kac-Moody algebra, and Borchardt conjectured already that all vertex generalized Kac-Moody algebras which arise in this nice way from string theory, that they are obtained by orbifolding the Leech lattice VOA or the moonshine module. And so the commutance W, which should occur in the even for the even sub VOAs of the self-dual supervertex operator algebra, should conjecturally all of this form, as I explained before, for some element in the convex group. Or you can take the moonshine module here. In this case, you have to take the 2A involution of the monster, which gives you something related to the shorter moonshine module. Okay, yeah, so that's so much I like to explain of our paper. Questions?
So this
Have
will be
you? Sorry,
like,
have you do you have any information on like trying to go get the n equals 1 like extend like the supersymmetric version? So basically looking for like the like weight 3/2 operators in the super
yeah.
algebras with
No,
right properties.
that's an interesting problem. I have a short paper with Jeff Mason, where we showed that when you just look at the lattice vertex operator superalgebras, which arise from Borchardt's classification of this for the odd unimodular lattices, that almost all of those have at least one n equal one supersymmetric structure, but we haven't looked yet if so my guess would be that most of our almost 1,000 vertex operator superalgebras have an n equal 1 structure. I know that I think here this for this vertex operator superalgebra Harvey Moore, not completely sure about the authors. They constructed an n equal 1 supersymmetric structure. So the answer is probably most, if not all, have an n equal 1 supersymmetric structure.
All right, thanks.
So this will be the first part of the talk. And audience, any comments, please feel free. And this will be take a short pause for now. Maybe let me ask something more. Can you step the assumption? So like maybe some statement constraint that you take in your approach. In the sense, I just want to make sure what series are classified under what constraint.
So yeah, for the vertex algebras, we're looking. I mean, when I say vertex operator algebras, they must satisfy some technical condition which I haven't mentioned. So we and then we look at them at central charge 24 or less, and we. The assumption is that they are self-dual. This really means that they have one irreducible module in the sense of vertex operator superalgebras.
So if you talk about CFTs, yeah, we would say we take a purely left-moving or purely right-moving CFT, yeah, two-dimensional CFT that's just chiral. It's a spin CFT or fermionic CFT. And then we make this assumption that it's roughly called rational in the physics literature, like a rational CFT. Yeah. So this is some technical assumption that mean that the representation category is well behaved. And then
one primary field. One primary field.
And then exactly. And then the most important assumption, this is the structural assumption, is that we have just one primary field. So this is what Gerald calls self-dual, or what's called meromorphic or holomorphic. So that's really the important assumption. Yeah. So yeah, purely left-moving spin, rational 2D CFTs with one primary field. I think that's what it would be.
This 1+1D CFT, at most, can only live on the boundary of 2+1D invertible TQFT, which is maybe some coordinate invariant or something, but it cannot live on the boundary of non-invertible TQFT, right? These are just 1+1D CFT on a boundary of either it's in 1+1D alone, or it's live on the boundary of 2+1D invertible TQFT. The 2+1D bulk cannot be non-invertible TQFT that people call topological order. Is that correct?
Yeah, did you understand?
Yeah, I'm not familiar with this three-dimensional boundary picture.
So I'm not quite sure.
Let's try to understand. Maybe I don't know. Yinshuan maybe know this. Yinshuan,
Yeah.
see.
I have a dumb question.
Yes.
Yeah. So if I have like very large central charge, is there any lower bound on like the largest gap you can get between like the first primary that's like not in the identity, like your shuttle sector?
Can you say that again? So okay, you're thinking of terms of central charge, and your question is,
so if I have a very very large central. I'm considering holomorphic CFTs and very large central charge. Is
Yes.
there a is there any lower bound for us? Like, how is there any lower bound for how extremely you can get? Like, is it possible to show that there exists at least one CFT where where there's a significant gap between the first primary of
that's an interesting question, and I think the best bound, more or less, I know is 12 or so. So I mean, for lattices and for codes, it's not so it's easy to construct codes and lattices with arbitrary large minimal weight or minimal norm. Now, for vertex operator algebras, one example is, and this is actually the large, for the largest minimal weight of a vertex operator algebra, which I know, is you take the moonshine module and then you take the fixed point under the action of the monster. And then and for this fixed point vertex operator algebra, the first non-trivial, which is not the comes not from the SVOA algebra, occurs in weight 12. And so I never really found any example where it could be larger. So my conjecture would be similarly to this bounds, like this Gilbert-Barshimov bound and now similar bounds which one has for lattices, that one also has lower bounds for vertex operator algebras. I discussed this a little in a recent paper on extremal vertex operator algebras, but I am not aware of any such result that one can get arbitrary large minimal weight for vertex algebra, independently of central charge also.
All right, thanks.
Okay, maybe I try sharing my screen and continue.
Yes, please.
So this only worked like partially when we did the test. So let's see. Am I now sharing my screen?
Yeah, but it's black.
It's black. And let's, yeah, so this is always the problem if you have Linux. Zoom only works. So is it still black?
It's still black.
Okay, so then we have the yeah.
Did you share the whole screen, or maybe
yes.
share the window?
I shared the whole screen.
Try to share just the window.
Yeah, this doesn't work. This option doesn't even appear in the Zoom. So I don't know what happened. I did an update and now it's not working properly. But Juven, I sent you the slides. Would you be able to share the screen instead of me?
I'm thinking even better, maybe Gerald can share the screen and
yeah,
and then you can help.
Gerald, then you maybe I can. I say
yeah. I have not the latest version, or did you send it also to me? Then
I forward it also to you. So
then
I apologize for this.
One minute. So then I can share it. Möller, the email. Okay. And yeah, what I have to download it. Download. Okay, save. Vortrag. Save. Overwrite. And then I have to display. It says ocular crashes. So let me try to use the PDFs instead, which I have. So I cannot get this PDF you are working with your file. It's too advanced, but I can at least make here this large as possible, full screen. I have to full screen, and now I have to share. Can you stop sharing your slides?
Yeah, this is not possible. Yeah, the button is disappeared. Yeah.
I can try to share my screen.
Yeah, you can share yours. Then you will kick me out.
Then desktop 3 share. Okay, and it is now. No, I think you're still sharing your screen.
Good. Then I need to.
So someone has to override. You have to disappear from sharing this.
I can restart.
Can you do that? Can you stop my sharing? Yeah, I apologize for this. It's this is annoying.
I don't think that I can stop this.
By your co-host.
I think I can.
Can you?
Let's see.
Your screen sharing live. New share. It has.
Yeah, thank you. Okay. Yeah, then that works.
Okay, so
okay.
And
I think
so
yes.
Okay, we are okay. Good. So then.
Do you want to go to full screen mode, Gerald, or just?
Yeah, I'm. This I can not, because the
okay, fine. Yeah, it's fine.
On your PDF.
I can see it. So I apologize again for the slight hiccup here. Yeah.
No, what is?
It's fine. Yeah. Okay, that's good, Gerald. Yeah, thank you. So I will continue with after Gerald's introductory talk. I want to give you a few more details. So some things I will say again a little bit in other words, but I think that's not a problem. And in the very end, I want to actually give you the result. I mean, okay, I will not be able to give you a full list. So we give a classification in a sense of almost complete. Yeah, there is again this issue with the uniqueness of the moonshine module. But apart from this, I will give you complete classification of the self-dual vertex operator superalgebras in central charge 24, and there are 969 of them. So it's impossible to list all of them in the slides. Okay, Gerald, can you go to the next slide, please? Yes, so this is roughly, and since we've talked about this before, but I thought maybe I spend 1 minute here again, because there is this picture. So Gerald started from codes. I will just pick up at lattices. So we have so as Gerald explained, we have the classification of the odd unimodular lattices of rank 24. You can classify them by looking at even lattices, and then the neighborhood graph. So the picture is this picture that's depicted here. So if you have, so on the N1 and N2 here are even lattices. And we say two lattices are neighbors if they share a common sublattice of index 2. But now if you have such a sublattice of index 2, you can extend it in 3 possible ways. And one of them will be, and this is if the rank of the lattice is a multiple of 8. Yeah, so this picture here only works if the rank is a multiple of 8. Yeah. Then one of these 3 extensions will be an odd lattice, and that's the L in the middle. So that's an odd lattice. And the other 2 are even lattices. And that's now where this picture comes from, right? So you have 2 even lattices are connected and by an edge, and this edge is labeled by an odd unimodular lattice. So this was the idea in the classification of the odd unimodular lattices. And let me say, essentially, rank 24 is as high as you can go. Yeah. So first you classify the even lattices, which is the Niemeyer lattices, which you can do in rank 24, and then from that, you as a starting point, you look at the odd lattices. Now, if you go to higher rank, it becomes untractable because already the even lattices, the number is way too big. Yeah. So you have over 10 billion even lattices in rank 32. So rank 24 is as far as we can go in any meaningful way. And the reason is, and Gerald already kind of alluded to this, the reason is that here everything is governed by the Leech lattice. So the Leech lattice is really the most special and the most peculiar lattice. Since recently, I mean, this was one of the celebrated results of Vyazovskaya and her co-authors. We know it gives you the densest sphere packing in 24 dimensions. And this was partially why she got a Fields medal. So this is the Leech lattice. You have to, if you remember one thing from the talk here, the Leech lattice is very special, and somehow it governs everything that happens up to rank 24. And we will see that this behavior still persists also for conformal field theories. Next slide, please. So this is again the picture of the neighborhood graph, as you can find it in Conway Sloan's book, but it's originally it was in Borcher's thesis. Okay, next slide. So what is the goal of the talk? And Gerald has already said this. So we want to classify a nice self-dual vertex operator superalgebras of central charge at most 24 by generalizing this neighborhood method. And this is so previously people attempted to do this and they got maybe to central charge 12 or 16 or something like this. But if you want to go higher, you have to use this neighborhood method. It seems, at least from what we have experienced, that the neighborhood method is the most effective method up to central charge 24. And after that, in any case, it becomes completely impossible to do a classification in the sense of listing everything. So it seems this neighborhood method is the most powerful method. And in physics language, again, what we are doing is we're looking at the purely left-moving or purely chiral spin or fermionic rational 2D CFTs that have just one primary field. We replicate this two neighborhood method, right? So for lattices, we had two neighborhood where we had for the same for codes where we have a common sublattice of index 2, and now we have to use a Z2 orbifold construction. And why were we able to do this now? I mean, Gerald started looking at this problem for his PhD in '95, so I was just barely born at the time. But now we have made advancement in orbifold theory for VOAs. We have a classification of the, so in this graph, we first need to classify the nodes. So these are the self-dual bosonic vertex operator algebras of central charge 24. And this has just become rigorous in recent years. And also we were able to determine the automorphism groups, and Gerald explained this in a bit more detail. So we almost know the automorphism groups, but we know them enough to determine this classification here. Next slide, please. Yeah, and then exactly. So let me, you can go to the next one. And so there are some subtleties when you define vertex operator superalgebras, in fact. So for us, so V, typically V, we use V for vertex algebras or vertex superalgebras. So you have this, so this is the state of space of your theory. And what we demand, and this is what I call correct statistics here, and you don't have to do this. You can look at fermionic theories that don't have this property, that the L0 grading, so the L0 operator or the translation operator, so the energy grading or spin energy grading that's determined by your translation operator or T, this should be integral on the even part, and it should be an integer plus a half on the odd part. In a sense, this is kind of a spin statistics statement. So this is something you can do for vertex superalgebras, but you don't have to require it. So this is just a somewhat technical point, but it has drastic consequences on the theory. So this is the kind of vertex superalgebras we're looking at. Okay, and then let me give you some examples of vertex operator superalgebras. And all of them actually happen to be self-dual or have just one primary field. So we have the free fermion. And physicists often call this BC system. But in fact, it's two free fermions. So the BC system is a tensor product of two free fermions where we just call F. And in fact, you can understand the free fermion as an extension of, so this L1/2 of 0, that's the Virasoro minimal model for PQ equals to 4,3, or the critical Ising model. Yeah, so this is something, of course, physicists know very well. So this is a CFT. And if you take the two simple currents that have weight 0 and 1/2, and you add them together, you can define on that an odd structure, a vertex superalgebra structure, and that's this free fermion F. And typically the square of F, so the tensor square, is what's called BC system. And then for any odd lattice, Gerald said this, you can take this odd lattice. So in general, if you have an odd or even lattice, you have an integral lattice, you can make out of this a VOA. Or in other words, what does this mean? So you have rank L many free bosons and you compactify them on a torus. And so then the momenta become discretized. And this is what's described by this lattice. And the boundary conditions somehow tell you whether this is even or odd, the lattice, and this corresponds to vertex algebra or vertex superalgebra. Okay. Okay, then one of the more prominent examples was also this, what Conway described, this super moonshine module, but in fact, it's just a lattice. But he also described the conformal structure on it. But if you just look at it as a vertex operator superalgebra, it's just a lattice vertex operator superalgebra for an odd integral lattice of unimodular odd lattice of rank 12. And then we have things like the shorter moonshine module, or the and maybe the last example is something that is often called. So there's a paper so there's a paper from in the physics literature from '88, which is quite famous. It's called the Beauty and the Beast construction. So if you remember, the moonshine module was constructed from the Leech lattice by doing a Z2 orbifold. And instead of going to the even extension, which gives you the moonshine module, you can do the odd extension. And that's this Beauty and the Beast vertex operator superalgebra, the corresponding string theory. Okay, next slide, please. Now we come, this was already asked a little bit, so let's come a little bit to some technical assumptions now. So now this is a bit mathematical, and when you study, I mean, what is so here our conformal field theories that we in the end classify, they are self-dual, so they only have one irreducible module, which is themselves. But in general, if you have a CFT, then how do you understand it? Well, you look at the chiral algebra, and strictly speaking, you also have to look at the anti-chiral fields. And those define, so what's called chiral algebra. That's in physics, that's what we call vertex operator algebra in mathematics. But this is not the CFT itself. You also have to look at the representation categories, which under some regularity assumptions, which I just call nice here. So I just say nice, but this is the word, you can replace nice by rational if you want. This is not exactly what mathematicians call rational, but this is what typically in the physics literature is called rational. Yeah. Then the representation category will be a modular tensor category. This is a result by Huang. And so here we're assuming that the vertex superalgebra is nice in this rationality sense. And then by some very strong results, this implies also that the even part. So when we have a superalgebra, then we can look at the even part. So this is just the bosonic fields in it. They define a vertex operator algebra. And this is again nice. So it has a nice representation category, which also means that the central charge must be rational. This is where the notion rational comes from, and it must be positive. And yes, so the representation category of the even part is a modular tensor category. And we can actually say quite nicely in mathematical terms how the representation category of the superalgebra relates to that of the even subpart. Yeah. And so what's written here, so so rep of V0, so that's a modular tensor category, which means in a certain sense it's non-degenerate. And then if you just look at so if you have a vertex superalgebra, you have untwisted fields and you have these canonically twisted fields, which are twisted by the parity involution. And both of them contribute to the fields. So over the even part of both of them become untwisted, because it's just over the even part, right? The even part doesn't see the parity. So then if you look at the representation category for the even part, it has two components. It's graded, Z2 graded. It has parts coming from the untwisted fields and parts coming from the twisted fields. And what I've written here on the bottom right of this blue box, the rep 0 of V0, that's the part coming from the untwisted fields. And this is not a modular tensor category because it's slightly degenerate. Well, I'll say to the experts in the audience, so non-degenerate means that your Müger center of your category is trivial, is vect, and this slightly degenerate, and I'm borrowing the notation here from a paper by Theo Johnson-Frade and David Reuter, would mean that the that the center, the Müger center, is S-vect. So it's this small. It's not quite trivial, but almost trivial. And what this leads to in our special situation, is this what was in the physics literature discovered by Kitaev. At least this is the first time I've seen it, and it's called 16-fold way. So the so this is okay, yeah. Okay, so this, I guess, this notation is somehow well known to category theorists, but it was somewhat new when I was reading up on this. And so if you have a self-dual vertex superalgebra, its representation category is vect. And if you look then at the representation category of the even part and only the contributions from, so then the VOA itself, the superalgebra splits in two parts, the even and the odd part, and those two become the element. So those two become the simple objects in your in the even part of the representation category of the even part. So this is S-vect as a modular tensor category, and then we know that the representation category of the full representation category of the even part must be what's called a minimal modular extension. Yeah, and in this special situation, this was observed by Kitaev, and then if you remove this assumption that the VOA, the superalgebra, is self-dual, you can still make the same statement. And then it's much harder. And then Lan, Kong, and Wen, what they showed is that if you have one minimal modular extension, you have 16. And then in a very nice paper by Theo and David, they actually proved that you always have such a minimal modular extension if you have such a slightly degenerate modular tensor category. So this was just an excursion. So what I want to tell you is essentially that if you start with a self-dual superalgebra, then the representation category of the even part is highly constrained. There's only 16 possible choices for this. Gerald, can you go to the next slide? And in fact, it depends on the central charge. So what you can prove is that the central charge of a self-dual vertex superalgebra, this is only true for self-dual. If you just say rational, you cannot really restrict it. But if it's self-dual, it has to be half integer. So the central charge has to be half integer. And if you take this number modulo 8, so then you have 16 possible choices for this number. This is in one-to-one correspondence with the representation categories that the even part has. Okay. And so all of these, so this is quite mathematical, but it tells you what the irreducible modules are, and it also tells you then how you can glue them back up together to get, for example, a vertex algebra again. And well, there's some case distinctions here, and maybe we can go to the next slide. So I have a table there. Yeah. So these are the 16 possible categories that can appear. Yeah. In the end, we will only look for this talk. In the end, the only thing we'll need is the first row, and you will recognize it from Gerald's talk. So this is when the central charge is a multiple of 8. It's 0 modulo 8. So then the representation category of the even part has this fusion structure of it's every module is a simple current, so it has group fusion, yeah, and it's Z2 times Z2 is the group structure, and we have conformal weight. So this defines a quadratic space. And if your central charge is a half integer but not integer, then you get Ising fusion rules. Yeah, so you get the fusion category of, well, if it's 1/2 modulo 8, you get the fusion category of the critical Ising model or the 3-4 minimal Virasoro minimal model. And for the other ones, it's a very similar one with the same fusion rules, but it has different twists or different braiding. Yeah? Okay, but in the end, we'll only need the first row of this. And the reason is that in all of the other rows, you cannot extend. I mean, you always have, you want to extend again to some even. So of course, this is inside of a superalgebra. So you will always have 0 and 1/2, right? Because those glued together give you a superalgebra. If you want to glue together to get a vertex algebra again, then you need weights that are integral. And this only works if the central charge is a multiple of 8. That's why we look at central charge multiple of 8. So this neighborhood method, this is a takeaway from this. This neighborhood method is just working when the central charge is a multiple of 8. Okay, let's go to the next slide. So this is, okay, and then even next one. So this then we have the neighborhood method, and Gerald already explained it. And this, again, but with the argument that I did, if we have a central charge which is if 8 divides the central charge, then we have this nice representation category of the even part, and then we can mimic exactly what happens for the lattices, namely that we have the even part of the vertex superalgebra has 3 possible extensions. 2 of them give you bosonic theories, 1 of them gives you a fermionic theory. And this is what we use to classify the superalgebras in central charge 24. And then because there is a certain splitting result, this gives us the classification in all central charges that are less or equal to 24. So it's not a problem to have to restrict to multiple of 8. So this is not a restriction in that sense. You can, if you do it for 24, you get it also for 22 and 23 and whatever. Yeah? Okay, let's go to the next slide. So this is the splitting result. Yeah. So if you have a simple vertex superalgebra, and okay, 2 more smaller assumptions, let's ignore this for now. So any vertex superalgebra, in a sense, you look at the fields that are generated by weight 1/2. And this will be, this you can show, this will be just free fermions. They cannot be anything else but free fermions, certain copies of free fermions. And the nice thing is you can split this off. Yeah. And so this means any superalgebra can be written as a tensor product of another superalgebra, which has no fields of weight 1/2, tensored with free fermions. And this, so we can always remove free fermions if we want, and then we are left with something that we call stump. Yeah, and maybe let's go to the next slide already. So rather than reading, let me show you this picture, what happens. So all self-dual, let's restrict to self-dual, but this works also for non-self-dual. Yeah, so all vertex superalgebras live in infinite families which are indexed by natural numbers. At the bottom, you have a stump, which has some central charge. And the condition for being a stump means you have no weight 1/2 vectors or fields. And then you extend your tensor product with a free fermion, your tensor product with another free fermion, and any VOA. So if you take an arbitrary VOA V, it must live in one of those infinite families and in exactly one of those. Yeah? So this is kind of the landscape if you allow the central charge to vary. Yeah. And that what this means is if you classify for a fixed central charge, you get a classification also for smaller central charge. Now, okay, we can go to the next slide. And doing this neighborhood method, this is now basically kind of a teaser. We want to do it for central charge 24, but this is for central charge 16. And by the way, this up to central charge 16, this was definitely known already in the string theory literature. So I will show you on the next slide, but let's first look at this picture here. So in central charge 0, there's only the trivial vertex operator algebra, and it has no, it's not super. So there's no super theories in central charge 0. There's only an even theory, no bosonic theory, right? And in central charge 8, you have the E8 lattice, which gives you an even theory, and that has an index 2 sublattice, which is D8, and that you can extend to D8 plus, which is a super lattice, which is an odd lattice. So this would be the unique self-dual theory in central charge 8. And then you can do it for central charge 16, where you have 2 bosonic theories, and they are connected in this way, and you get 7 fermionic theories. And the point I want to make here is we have this injection from the lattice neighborhood graph into the VOA neighborhood graph, and for central charge 0 and 8, they are identical. For central charge 16, the nodes are lattice nodes, but from the edges, there will be one additional edge that's not a lattice edge, and this is one that's dashed in this picture. Yeah, so this is a permutation orbifold. This is not, or we would say it's a West-Mitten model for E8 at level 2. So it's not level 1, so it can't come from a lattice. It's level 2. And then in central charge 24, we have many nodes already that are non-lattice nodes, and even more edges that are not lattice edges in this sense. Okay, let's go to the next slide. Yes, okay, so here we just list them, and this is just this perspective. Now, if you've classified in central charge 16, you can now extend this classification down, and we have on the right-hand side, we have these stumps. Yeah, and that means, so the lowest number here that's not 0 is 8, right? But 8 is actually this. In what can happen is that the stump actually becomes a bosonic theory. So the smallest truly self-dual theory that's not just copies of, fermionic theory that's not just copies of free fermions will happen in central charge 12, where it's this D12 plus lattice or the super moonshine module. Yeah. All other ones are either just copies of free fermions, or you take the E8 lattice, which is actually bosonic theory tensored with free fermions. But suddenly the complexity becomes much larger if you go above 12, and then higher than, if you go even higher up to 24, it gets much, much more complicated. Okay. And let's go to the next slide. So let me just show you that this has been known, not in the sense of a rigorous classification, but these theories have been known already in the string theory literature. So this is from a paper from 86, and they give also the it's nice because they give the reference to the different places where these things have been considered. And the green box here, that's the bosonic theories, and so that's 2. We have E8 times E8, for example, and then in SO32 that's D16, right? So that's just a relabeling. So D and SO, and then the red box, that's the corresponding, that's the 7 super theories that it had in the previous picture. So that's just and here it's written in kind of different words. So I guess this is kind of more approachable maybe to the physicists in the audience, yeah, because of course as CFT somehow they correspond also to string theories. Yeah? So this has up to 16, even though it was not a rigorous classification, it has already appeared in the string theory literature, corresponding to 10-dimensional somehow, yeah, 10-dimensional superstring theories. Okay, let's go to the next slide. So this Gerald has already explained, so we can go over this briefly, and also I don't want to extend this talk too much, but let's have briefly, let me recap this. Yeah. And well, I say it in my words. So when you have, this works for any vertex algebra, and it also works for superalgebras in a similar way. We can write the internal structure in a certain way, right? So we take this Lie algebra that's generated by the weight 1 field. So before we had the weight 1/2 fields, and we were able to split this off. Now with the weight 1 fields, it's a bit more complicated. We cannot completely split them off, but they will still tell us a lot about the internal structure. And this is what Gerald already explained. So we have this maximal lattice theory that's sitting inside of any theory that we look at. Let's assume it's rational again. Yeah. The only point is now that this lattice, the rank of the lattice is smaller than your central charge. So it's not a conformal embedding. To make this a conformal embedding, you have to take the tensor product with the commutant. So you have this dual pair, U and the lattice. So U is this Heisenberg commutant, and coset. It was originally, I think, in the physics literature, it's called coset construction. So you have this tensor product of U and the lattice, VOA, VL, and you can view your VOA, and this is completely general, as an extension. It's actually a simple current extension of this dual pair. You look at the representation category of this dual pair, and you can study your any theory as an extension of this. So this is this point that Gerald was first using, and there's also a paper by Mason from 2014 where he kind of studies this maximal lattice VOA. So this is okay. Let's go to the next slide maybe. And now this looks a bit complicated, this slide. So this is something I have to explain briefly. So Gerald was explaining the situation when your VOA is self-dual. Yeah. Then you have this braid reversed equivalence between these two representation categories, and when you glue along this braid reversed equivalence, you get something that's self-dual. But now we look at the even part of a self-dual superalgebra, which itself is not self-dual, but it has this representation category that has 4 irreducible modules. And now when you glue, yeah, there are several cases that can happen. So the representation category of U and the lattice part, they have to be roughly the same, but not quite. They can differ by a factor of 4. And depending on which one is bigger, or if they're the same, you have 3 or actually 4 different cases. And well, I think this is a bit too much information on the slide to grasp in such short time. Let me just say, this gives you a way of kind of subdividing this big classification where we get roughly 1,000 superalgebras into 4 subcases. And in this two neighborhood perspective, it corresponds to certain properties of the automorphisms that you are considering. So this is, I guess, a slide for the experts in a sense. Sometimes you have inner automorphisms, sometimes you have non-inner, and so on. Yeah. So maybe in the question we can come back to this detail, but for now let's just say, okay, we have certain ways of gluing to get such a self-dual vertex operator superalgebra as such an even part of a self-dual superalgebra. And that leads to a natural subdivision of our cases into 4 different cases. Let's maybe go to the next slide then. So let me come to the classification results. So let me reiterate. So how do we do this classification? I will not. It's in the end. It was a lot of work because in the end it's a lot of computation. So the idea is very clean. It's to use this neighborhood method, but in the end you have to actually sit down and do a lot of computations. Yeah? And we have 2 approaches. Yeah? We use this orbifold approach because we have almost this classification of the even ones. These are these Srelikens VOAs where there are 71 plus possibly fake copies of the moonshine module. And we consider Z2 orbifolds. And then because we are not, as Gerald said, we in most cases we can fully understand these automorphism groups, but not in all cases. We only get an upper bound. I mean, if you could do this perfectly, you would be done at this point, right? You have all the nodes. On all the nodes, you have the automorphism groups. You determine all the order 2 automorphisms. This gives you the edges, and you are done. But we only can do this, let's say, up to 95%. That's why we need to have the second perspective where we describe these superalgebras as this simple current extension of this dual pair. And with a combination of those 2 methods, we can actually give a complete classification. So this is unfortunately a bit technical, but it's in the end what we had to do. But a nice result, a quite nice result is that, again, everything comes from the Leech lattice. And let me make this more precise. But if there's one sentence you remember from this talk, is up to central charge 24. Everything comes from the Leech lattice and also the monster group in a sense. Yeah? So this theorem that's written in this box, Gerald had already written. So this is if you take the bosonic theories in central charge 24, then you have this. We have this decomposition into a lattice part and to this Heisenberg commutant. And it turns out that this Heisenberg commutant, there are not many choices for this. So you have, in principle, this could be very wild, but it somehow turns out that all of these Heisenberg commutants can be described in terms of, there are 12. One of them is the moonshine module. So in this case, there is no lattice, which means everything is just this Heisenberg commutant, and it's the moonshine module. So there is no lattice in the moonshine module. This is what makes it a bit hard to work with the moonshine module. In all of the other ones, you have a lattice. The rank may be small, but you do have a lattice. And then the complement of this lattice is a non-lattice vertex algebra. And this is what we call Heisenberg commutant, but it still comes from a lattice. And this is surprising in a sense. It comes from a lattice, but you have to do an orbifold. Yeah? In fact, it corresponds to certain elements of the automorphism group of the Leech lattice is the conway group, and it corresponds to certain elements, very nice elements in this conway group, 11 conjugacy classes in this conway group. Yeah? So let me reiterate, in the self-dual vertex operator algebra, so this is the bosonic case, there are 12 different commutants, Heisenberg commutants appearing, and except for the moonshine module, all of them come from the Leech lattice in a certain well-understood way. And for the superalgebras, this gets extended a little bit. So we had these 4 cases. In case 1, case 2a, and case 2b, because this corresponds to inner orbifolds. Inner orbifolds cannot touch the commutant. So they cannot change it, which means the same statement is still true for those cases. But we had also case 3. These were outer automorphisms or non-inner ones, and they can change the commutant, which leads us to the next slide. Which is the, okay, this we have seen already. Let's go to the next slide. So this is now the corresponding statement for the fermionic theories. Yeah? And here now you have, so the old commutants can still appear, but you have new commutants appearing. Namely, you still have one that comes from the moonshine module. You take the 2a involution of the monster, let it act on the moonshine module. So this gives you one. And then again, because the uniqueness of the moonshine module is not known, we also don't have the uniqueness of this of this orbifold of the moonshine module. So this is again, our classification will be rigorous with this one exception. We don't know whether there are fake copies of this 2A fixed points of fake copies of the moonshine module. And then you have new, and all the other commutants again actually come from the Leech lattice. So this is again quite surprising that what we had in the bosonic case is still actually true in the fermionic case. I mean, maybe Gerald knew this all along, but to me it was somehow surprising. So now instead of having 12 possible Heisenberg commutants, we have 19 plus this one fake, plus these fake copies that we cannot exclude of this one case T, right? So naturally all of these superalgebras that we list in our paper, 969, they fall into these 19 families, which we label by letter A to T without the letter L. And yeah, really, this is kind of the takeaway. Why can we classify it in central charge 24? It's because the Leech lattice is able to govern what happens. If you go to central charge 32, it will be completely hopeless. Yeah, there's no way this can ever be done. Certainly not in my lifetime. And so this breaks, all of what we are doing here is breaks completely down in higher central charges, right? Okay. So so again, Gerald gave this list of 11 commutants, and we list here the representation categories, and all of them are pointed. So this pointed means all of the modules, all of the irreducible modules are simple currents. So this is what mathematicians call pointed representation categories, and they're modular tensor categories. And they're pseudo-unitary and have all of these nice properties. And we know that they are in one-to-one correspondence with the non-degenerate finite quadratic forms. I mean, quadratic forms on finite abelian groups, so this is this abelian 3 cohomology theory by Eilenberg and MacLean from the 50s. Yeah? And well, so we first do this, we do our orbifold procedure, and at least what we're able to do is we can say we have these 19 Heisenberg commutants, and we get a slightly too big list. And then we can do, because we now have the commutants, we can do the extension picture coming from below, and we can give a precise list of what should be the vertex superalgebra. So let's go to the next slide. And this is the theorem then. So we obtain 969 vertex operator superalgebras in central charge 24. To make this a rigorous statement, we have to exclude this one case. And the property it has is that it has no weight 1 space. So it has no weight 1 elements. And also the canonically twisted module has no weight 1 element. So this is the module that's twisted under the canonical involution, which is the parity involution. Yeah. And so this one we have to exclude. But if we exclude this, then we have 968 nice self-dual vertex operator superalgebras. Okay, there's this one more case which exists, but we don't know whether it's unique. And so this is what's written then below. Yes, so that there may be fake copies of this. And so there's a question in the chat if there's a combinatorial explanation of the 969. Not that I'm aware of. Yeah. So I mean, I'm not aware of any nice combinatorial explanation for this number. Yeah. So if you look at the paper, there's these 19 families, and each family has a certain number, and it's just, to me, this looks just like arbitrary numbers. So I have no, I don't see any combinatorial explanation there. Yeah. Already in the bosonic case where you have 71, we don't really know whether there is a nice answer here, but maybe Gerald can say a little bit about this later. Okay, let's go to the next slide then. So then there's the question. So I promise I'm done in a minute. I don't want to go too much over time here. Yeah. So there's the question of the neighborhood graph, and this is one point I want to make. In the lattice case, there is a theoretical result that says that the neighborhood graph is connected. If you look at, has one connected component. Yeah? So if you look at all this, the unimodular lattice, actually in any, I mean, even unimodular lattice is positive definite, and you can drop a lot of these assumptions, but that's fine. Then they are connected by two neighbors, and actually any p neighbor. So you don't have to do it for two; you can do it for any prime. So this is connected, and this is not true anymore for vertex superalgebras or vertex algebras. So here I cannot give you the whole neighborhood graph because putting 70 nodes with 1,000 edges you will see nothing. So we zoom out a little bit and only look at these 19 families. And actually on the level of the bosonic theories, we had 12 families. So the nodes here are now these complete families, right? So each node here corresponds to many actual theories. I mean, not many, but so we have 71 theories that we put into these 12 macro nodes. And we have edges between them if there is an edge between the micronodes. So we just now look at this Heisenberg commutant, which gives us, this into these families. And you see here that it has 4 connected components. And this is actually still true if you look at the actual neighborhood graph. So the neighborhood graph for the VOAs for p equals to 2 has 4 connected components. If you allow all the possible orders, it probably becomes connected again if you mix different orders. Yeah? But if you just have one order 2, it's not connected. And if you go to the next slide, this was already observed a long time ago by Montague. So he only looked at kind of plausibility arguments. He was only looking at the Lie algebra structure that plays an important role, but certainly doesn't tell you everything. And already looking at the Lie algebra, you can sometimes rule out that there is an edge connecting 2 points in this neighborhood graph. And already he saw that this has definitely more than one connected component, this graph. So this is arguably very partial results, but already conceptually nice because he saw that this neighborhood graph has more than one connected component. So this was by Montague in 97. Yeah. Okay, let's go to the next slide. So I think this is my last slide. Yeah. So let's look at the last line on the right-hand side. So this is the number. So we have vertex operator. I want to just give you the numbers, right? We can't give you the whole list. This is too long, but let's give you the numbers. So we have 969 odd theories or vertex operator superalgebras. Now, we also have even theories. There's 71, and the brackets or the parentheses mean that this is only true up to this uniqueness of the moonshine module. All numbers that are not in parentheses here are rigorous. And then you can populate this table by splitting off free fermions. So going from 24 to 23.5, you just split off whenever it's possible. You split off free fermions and so on. And you can go all the way up to 0. And then and on the right-hand side, I give you also the corresponding number for lattices. So you have this is this famous result by Borchers. You have these 273 odd unimodular lattices in rank 24, for which Gerald says we know that there's this n equals to 1 supersymmetric structure, and for the other ones we haven't looked at this rigorously. So this is kind of the classification result. I think let's see that this should be my last slide, right? Can you go to the next slide? Yes. So thank you for your attention. And thanks for doing the slides, Gerald. Sorry about this technical issue.
Thank you very much. Your best. Vielen Dank. Thank you, Gerard and Sven, for the wonderful seminars. Any question from the audience?
Yeah, thanks for the great talk. Is there any chance of there being some kind of like version of the Siegel mask formula for these like crowd CFTs?
Yeah, this Gerald should answer.
Yeah, so 2 weeks ago, I wrote to Sven that there is probably not, I mean, the general thing is the answer is no, because almost all of the vertex operator superalgebra have infinite automorphism groups. So you cannot directly take the order of the automorphism group. So my idea was that one, instead of looking at the whole automorphism group, one looks essentially at the it's a lattice part of when you it's a decomposition into the lattice VOA and the Heisenberg commutant, and then you take this one. And so what my suggestion is, and that for each of these, what was it, 19 families, that there is type of a lattice type mass formula. But I didn't get, we didn't really work this out, although we have all the numbers in the computer. Now, in general, there is, it's unclear, and probably the answer is no, that for vertex operator algebra, there is such a mass formula. But somehow, if you just look at the lattice aspects, which there is a lot in our classification, then one gets this type of mass formula. Interestingly, when I sent Borchardt the announcement of this talk, and then he asked me exactly the same question. Actually, he suggested that one should generalize his approach, because what he did, although I'm not sure if it's explicitly in his thesis, is that when you look at this neighborhood graph and you fix one node, so one self-dual vertex operator algebra, and then you look at all the edges which start at this node, and you know the automorphism groups of these edges, then you they are in relation to the order of the automorphism group of this particular node. So you get, in the lattice picture, you have 24 partial mass formula, and actually Borchardt used this to check his result in his thesis, and I believe something similar we can do in the vertex operator algebra picture, although it's not quite a mass formula for vertex operator algebra.
All right, thanks. Can I ask just one more?
Of course.
I've been asking everyone I can about this question, which is who knows anything about vertex operator algebras, which is, do you know of any way one might try to formalize the notion of like a non-invertible topological defect line for one of these chiral CFTs? Because it seems like these kind of things will provide some very like intricate algebraic geometric objects associated with these chiral CFTs.
Yeah, I don't know the answer to that. Maybe Theo in the audience knows. I mean, he knows more about TFTs, but I'm not sure.
I mean, roughly, like if you're looking at a holomorphic theory, then you should say that the data of giving a fusion category action on it should be the same as the data of like a sub VOA, so that the whose representation category is center of your fusion category. And then there's probably some technical details that would have to be said correctly.
Thanks.
Okay.
Yeah, I also saw that. So Theo asked a question in the chat, so let me read this. So a lot of the lattice story can be coded in terms of a single lattice that's not positive definite anymore, but it's now has a Minkowski. I mean, it has signature 25,1, and so that's and the question is, can we do something similar here? And the answer is, I mean, there's two answers. So we can tensor with, we can take everything we have and we can tensor with the 1,1 hyperbolic plane, so the unique unimodular lattice of signature 1,1, but it will not connect these different families. So that's kind of the problem. You stay within these 19 families, and then it amounts to something similar to what Gerald said, that you stay within these families, and there you maybe have a mass formula, but it doesn't connect everything. And so there's so this is not in a sense so this cannot be like the final answer. So maybe one has to actually do this in the setting of actual conformal field theory, where you have left and right moving fields, maybe something like this. And then you have deformations that go from So from one to the other. So the Moriwaki was looking at this a little bit. But just tensoring with like copying what's done in the lattice case and tensoring with this hyperbolic lattice, yeah, it doesn't completely work. So, but that's a very good question. Yeah? If you have an answer to this question, this may give yet another approach to doing these classifications, yeah, which may be even more powerful.
Yeah, let me say something for this. I mean, as I showed in my slide, so I think the analog for vertex algebra is this generalized Kac-Moody-Lie algebra, which you get by tensorizing essentially the hyperbolic plane or rescale hyperbolic plane in the vertex operator superalgebra picture. So the question is, what are all the bosonic string theories which you can get from such a vertex operator algebra approach? And the conjecture by Borchardt is that essentially they came all by obifolding the generalized Kac-Moody-Lie algebra for the fake monster Lie algebra, which you get from the Leech lattice, and the monster Lie algebra, which you get from the moonshine module. So in this sense, somehow this also there is maybe some hope that you from this picture at least, I mean, it's just a conjecture that you get a somewhat more uniform combinatorial description of this vertex operator superalgebra. But let me mention one more thing. This was another question in the chat before. So for the self-dual vertex superalgebra, I gave in my 2007 paper a nice combinatorial description in terms of the 24 Niemeyer lattices. So for the even self-dual vertex operator algebra, there is a nice combinatorial description, but we were not really able to do this also for self-dual vertex operator superalgebras.
Yeah, you're right. Of course, I should have mentioned that. Yes, thank you.
Any other question, comments? In any case, I think we should give a big thank you to Gerald and Sven again for the wonderful lecture and seminars. Thank you very much. Vielen Dank. Thank you.
Yeah, thank you. Thank you for the invitation. Obviously, yeah, it was a pleasure. And your German is very good.